Some architectural masterpieces were not built for their own time. They contain secrets that defy our understanding of history. This is the story of the architects who broke the rules, visionaries who embedded futuristic concepts into stone and mortar centuries ahead of their time. By the end, you will understand how ancient innovations are shaping the buildings of tomorrow. How did a dome in ancient Istanbul seem to float on light? Why does Roman concrete last longer than our own? We will uncover the hidden genius behind structures that baffle modern engineers. What does it truly mean to build for a future you will never see? Breaking the architectural rules of one's era is a quiet act of revolution. It is not a simple act of defiance for its own sake, but a fundamental reimagining of what is possible. These figures looked at the stone, wood, and brick available to them and saw something entirely different than their peers. They confronted the established methods, the trusted techniques passed down for generations, and asked a dangerous question. What if there is another way? This pursuit often came at a great personal cost, met with skepticism from patrons and ridicule from fellow builders. Yet, their conviction led them to embed ideas into their work that were completely alien to the contemporary understanding. They employed geometric principles that would not be formally defined by mathematicians for centuries. They designed structures that interacted with sunlight, wind, and water in ways that prefigure our modern concepts of sustainable design. Their rule-breaking was not merely a surface-level change to a facade or a decorative style. It was a deep, philosophical shift that rethought the very relationship between a building, its inhabitants, and the natural world. By daring to challenge the bedrock conventions of their time, they created portals to the future, leaving behind a legacy of Chinese letter, Chinese letter, Chinese letter, Chinese letter, or forward thinking that we are only now beginning to fully decipher. This foundational spirit of innovation sets the stage for our first concrete example, a building that seems to defy the very laws of physics itself. That spirit of revolution finds its first great voice in a man named Imhotep. He stood before the Egyptian desert sands nearly 5,000 years ago and saw not just a royal tomb, but a mountain of stone reaching for the gods. Before Imhotep, pharaohs were buried under simple, flat-topped mounds of mud brick known as mastabas. These were humble, earth-bound structures. Imhotep, serving Pharaoh Djoser, dared to imagine something monumental and eternal. His radical idea was to stack 6 of these mastabas, each one smaller than the last, creating a colossal, stepped pyramid that dominated the horizon at Saqqara. This was not merely an enlargement of an old design. It was a complete reinvention of form and ambition, a fundamental break from tradition that shifted construction from perishable mud brick to the enduring strength of cut stone. The step pyramid was far more than a tomb. It was a complex statement, blending deep spiritual meaning with groundbreaking engineering. Its layered, ascending tiers were explicitly designed as a staircase to the heavens, a physical pathway for the pharaoh's soul to climb and join the eternal gods. This powerful symbolism was made possible by techniques that were centuries ahead of their time. Imhotep and his workers mastered the art of quarrying, transporting, and precisely positioning massive stone blocks. They understood concepts like load distribution, using carefully placed packing stones and an inward sloping structure to ensure stability, preventing the immense weight from causing a collapse. Think of it like building a layered cake, where each tier must be perfectly centered and supported to hold the one above. He was engineering on a scale never before attempted, solving problems of physics that his contemporaries had never even encountered. Beyond the stone itself, Imhotep's genius extended to the very organization of the project. To build the step pyramid complex with its surrounding temples, halls, and courtyards required the coordinated labor of thousands of workers over many years. This was not a chaotic effort. It was a meticulously planned operation that foreshadowed modern project management. Imhotep had to manage quarries, logistics, housing, and feeding a vast workforce, all while maintaining a singular artistic and structural vision. He was not just an architect, he was the world's first known master builder, a CEO of construction, proving that a great building requires both a brilliant design and an even more brilliant system to bring it to life. How did one man's vision lay the groundwork for millennia of architectural evolution? By refusing to be bound by the limits of his time, Imhotep did not just build a pyramid. He created an entirely new paradigm for what humanity could achieve with stone and ambition, setting a precedent that would echo through the ages and lead us directly to another structure that seemed to defy gravity itself. Centuries later, and a world away from the sands of Egypt, another architect was engaging in a different kind of rule-breaking, one that manipulated not just stone but the human eye itself. High on the Athenian Acropolis, the Parthenon presents itself as a monument of perfect straight lines and rigid geometry, but this is a magnificent deception. Its architect Iktinos understood something profound that builders would forget for over 1,000 years. He knew that mathematical precision does not always translate to visual perfection. To our eyes, truly straight lines can appear to sag, and flat surfaces can seem to hollow out. So Iktinos fought perception with geometry, embedding a series of subtle, brilliant distortions into the marble to create the illusion of flawless perfection. Look closely and you will see that none of the Parthenon's columns are actually straight. They bulge almost imperceptibly in the middle, a technique called entosses, which counteracts the optical illusion that a straight column would look pinched at its center. Furthermore, the columns are not planted perfectly vertical. They all lean inward slightly, and the entire platform they stand on curves upward in the center. If you extended these lines upward, they would eventually meet more than a mile high in the sky. This was not a construction error. It was a calculated masterpiece of visual psychology. These curves make the massive temple feel dynamic and alive, preventing it from appearing static or boxy from a distance. The entire structure is also a tapestry of mathematical harmony, woven with ratios like the golden section. This proportional relationship found throughout nature is inherently pleasing to the human brain. Iktinos embedded it in the relationship between the temple's length and width, the spacing of the columns, and even the dimensions of individual architectural elements. He was engineering an experience, not just a building. This deep understanding of aesthetics and perception suggests a knowledge of geometry and human vision that was UTTERL, Chinese letter, Chinese letter, Chinese letter, Chinese letter, or forward thinking. The genius of these refinements may even have a structural purpose. The slight flexibility introduced by the curves and inclines could have helped the Parthenon withstand the test of time, including numerous earthquakes, by allowing the structure to sway and dissipate energy rather than remaining rigid and brittle. This intuitive grasp of dynamic loads in stone is something modern engineers still study. The lesson from the Parthenon is that true mastery lies in knowing when to break the rules of literal measurement to serve a higher truth of human experience. This pursuit of manipulating perception within a space leads us to consider how other cultures sought to control an even more elusive element, the very sound within their sacred walls. While the Greeks perfected the art of visual illusion, the Romans mastered a far more tangible kind of magic, one locked within the very chemistry of their building materials. Across their sprawling empire, Roman architects engineered a substance that seems to defy the natural order of decay, a concrete that could not only set underwater but actually grow stronger for centuries. Modern concrete, by stark contrast, begins to deteriorate after just a few decades, especially in harsh marine environments. The secret to this ancient superiority lay in a revolutionary recipe that broke completely from tradition. Instead of relying solely on the strength of cut stone, Roman builders embraced a versatile mixture of lime, volcanic ash, and rubble. This was not a simple paste. It was an engineered chemical reaction waiting to happen. The key ingredient was the volcanic ash, particularly from the town of Pozzuoli. When this ash, rich in specific minerals, was mixed with lime and exposed to seawater, it triggered a long-term chemical process. Tiny plate-like crystals would slowly grow within the concrete, filling in microscopic pores and cracks. Imagine a structure that possesses its own immune system, one that actively fights back against the wear and tear of time. This is precisely what the Romans achieved. Their concrete was not a passive material. It was a living, breathing matrix that healed itself. This self-healing capability is a concept that modern material scientists are only now beginning to replicate in our quest for sustainable building supplies. With this almost miraculous material at their disposal, Roman engineers were unleashed. They could dream on an unprecedented scale. Their most breathtaking application is the majestic dome of the Pantheon in Rome. Cast in place nearly 2,000 years ago, this vast, unsupported dome remains the largest of its kind in the world. It is a single, monolithic shell of Roman concrete, a testament to their profound understanding of both material science and structural form. The concrete used at the top of the dome was progressively lighter, mixed with porous pumice instead of heavy stone, demonstrating a nuanced grasp of weight distribution that would challenge engineers today. How did a civilization without electron microscopes or chemical formulas develop such an advanced material? The knowledge was likely born from meticulous observation and generations of practical experimentation. They saw how certain volcanic materials reacted with water and lime, and they had the vision to systematize that reaction into the backbone of their empire. Yet, this revolutionary knowledge, like so many Chinese letter innovations, faded with the empire itself. The precise formula and the understanding of the complex chemistry were lost for over a millennium. The legacy of Roman concrete forces us to ask a profound question. How much of our own modern advancement is truly permanent? Their resilient construction did not just shape buildings. It shaped the very infrastructure of civilization, enabling harbors, aqueducts, and bridges that connected and sustained an empire for centuries. This mastery over material and form, however, would face its ultimate test in a different era, when one medieval builder attempted to reach a height that logic said was impossible. That mastery over material and form would face its ultimate test in a different era, when one medieval builder attempted to reach a height that logic said was impossible. But before we arrive at those stone forests of Gothic Europe, we must witness a different miracle of weightlessness in the heart of Constantinople. The Hagia Sophia presents a paradox, a structure of immense stone and brick that feels as though it could float away on a sunbeam. Its great central dome does not simply rest upon the building. It appears to hover, magically detached from the earthly realm, a golden hemisphere suspended by a ring of light. This breathtaking illusion was the work of architects Anthemius of Tralles and Isidore of Miletus, who broke from the established rules of Roman dome construction to solve a fundamental problem. How do you place a massive circular dome securely on top of a square base? Their revolutionary answer was the pendentive. Imagine a curved, triangular piece of masonry, like the rounded corner of a cushion that has been squashed down. The architects built 4 of these pendentives in the upper corners of the square space, and upon these 4 graceful, curved triangles, they perfectly seated the circular base of the dome. This was a geometric and engineering breakthrough of staggering importance. It was a seamless transition from a square room to a round dome, eliminating the need for the heavy supporting walls that had defined Roman architecture. Suddenly, the interior space could be vast, open, and uninterrupted, a single, unified volume that soared upward. To amplify the feeling of divine suspension, Anthemius and Isidore perforated the very base of the dome with 40 windows. When sunlight streams through, it creates a continuous band of brilliance, a halo of fire that visually severs the dome from the walls below. Your eye cannot find a solid point of connection. It seems to rest on light itself, an effect that masterfully merged profound spiritual symbolism with audacious structural genius. This was not just a building. It was a theological statement written in stone and illuminated by heaven. The architects further ensured this heavenly vision would not collapse under its own weight. They incorporated ribs within the dome's shell and used exceptionally lightweight bricks and a special porous mortar, creating a structure that was both strong and remarkably light for its size. They were distributing weight and managing forces with an intuition that anticipates the thin shell concrete structures of modern stadiums and airport terminals. Even the acoustics were part of the design. The dome's precise curvature and the hard, reflective surfaces worked together to create a long reverberation time, allowing chants and prayers to swirl and linger in the air, enveloping the congregation in a cloud of sound. What inspired these 6th century minds to blend art, science, and spirituality so completely? They were building a new vision of heaven on earth, and that ambition demanded they rewrite the architectural rules of their time. This Byzantine fusion of form and function, of light and structure, would echo for centuries, setting the stage for a new generation of rule breakers in the West who would push the boundaries of height and light even further. That Byzantine ambition to build with light found its ultimate expression in the stone forests of Gothic Europe. There, a new generation of architects performed what seemed like an architectural miracle, turning solid walls into shimmering curtains of colored glass. At the heart of this revolution was a seemingly impossible goal: to construct buildings of unprecedented height that were not dark and heavy, but luminous and weightless. The key to this paradox was a structural innovation that broke every established rule: the flying buttress. Imagine a stone arm reaching out from an exterior pier to catch the outward thrust of a massive roof vault, like a friend bracing your back as you lean over a ledge. This external skeleton of arched supports allowed medieval masons like the enigmatic Villard de Honnecourt to do the unthinkable. They could remove the thick, fortress-like walls of the older Romanesque style and replace them with vast, delicate panels of stained glass. The walls no longer had to bear the immense load the flying buttresses did. This transformed the cathedral from a solid mass of stone into a fragile-seeming cage of light, a symbol of heavenly Jerusalem descending to earth. Inside, the effect was breathtaking. Sunlight, filtered through countless pieces of colored glass in brilliant blues, reds, and golds, would flood the cavernous space, painting the interior with a divine, ethereal glow. This was architecture as spiritual alchemy, turning physical stone into an experience of transcendent light. But the innovations did not stop at the buttress. Overhead, the ceiling was a marvel of stone carpentry. Ribbed vaults with their intersecting stone arches created a skeletal framework that channeled the weight of the roof along precise, elegant lines down to the columns and piers below. Think of the difference between a solid slab of concrete and a geodesic dome. The ribs make the structure incredibly strong while using far less material. This entire system, the flying buttresses outside and the ribbed vaults inside, formed a complete structural skeleton. It was a radical departure from thinking of a building as a collection of walls and instead envisioning it as a dynamic framework of balanced forces. How did these craftsmen, often working without formal engineering training or detailed blueprints, achieve such staggering heights? Their knowledge was empirical, passed down through guilds and refined through daring, sometimes catastrophic, experimentation. They learned by doing, by observing what worked and what collapsed, developing an intuitive grasp of physics that allowed them to push stone to its absolute limits. The intricate geometry of the rose windows and the pointed arches were not merely decorative. Their complex patterns distributed forces efficiently, turning potential weaknesses into elements of strength and beauty. This fearless pursuit of verticality, of reaching for the sky with a framework of stone and light, directly prefigures the steel skeletons that would allow our modern skyscrapers to scrape the clouds. The Gothic masters proved that true innovation arises from a marriage of visionary ambition and practical necessity, a lesson that would soon be embraced by a new breed of artist engineers who sought to unite the entire cosmos within a single, perfect building. While Gothic architects were pushing stone to its vertical limits, a different kind of challenge was brewing in Florence. The city's new cathedral stood proudly, yet for decades its most crucial feature was missing, a gaping hole in its roof waiting for a dome that everyone said could not be built. The span was too wide, the walls too high, and the conventional method of construction, using a massive wooden support scaffold, was deemed too costly and complex. The project was a public puzzle, a testament to failed ambition, until one man stepped forward with a radical vision. Filippo Brunelleschi was not a typical builder. He was a goldsmith and a clockmaker, an outsider whose mind was unburdened by the strict traditions of architecture. He stared up at that unfinished space and saw not an impossible problem, but a geometric and structural riddle waiting to be solved. His genius lay in rejecting the known paths of both Roman and Gothic engineering to invent a completely new system. The result was a double-shelled dome, an ingenious structure within a structure. The inner shell was thick and robust, designed to provide the primary strength, while the outer, thinner shell served as a protective weather shield while also contributing to the overall form. The space between them created a network of passages and stairs, reducing the total weight dramatically. But the true magic was in how he built it. Brunelleschi devised a revolutionary herringbone brick pattern, laying the bricks in a spiraling, vertical sequence that locked each course into the one below. Imagine building an arch on its side where each brick is angled inward, creating a self-supporting spiral that grows upward without needing a temporary wooden frame. As the masons laid each ring, it would set and harden, becoming a stable base for the next, a continuous process of construction that was also its own scaffolding. This was a profound manipulation of tension and compression, using the brick's own weight and arrangement to create a stable, cohesive whole. To make this audacious plan a reality, he had to invent the tools for the job. He designed extraordinary hoisting machines powered by oxen that could lift massive stone and brick loads to unprecedented heights, machines that incorporated reversible gears and other innovations never before seen on a construction site. He even developed new mathematical techniques to precisely calculate the dome's complex curvature, ensuring every brick was placed exactly as his vision demanded. The dome spanned 45 meters, a vast expanse achieved without a single internal support, a feat that still inspires awe today. What drove Brunelleschi to risk his entire reputation on such an audacious and unproven method? It was a fusion of creative brilliance and sheer courage, a willingness to trust in his own geometric logic over centuries of established practice. His work demonstrated an early, almost intuitive grasp of circular stability and material behavior under stress, concepts that would take formal shape in civil engineering hundreds of years later. He proved that beauty and innovation were not separate pursuits, that the most elegant solution could also be the most structurally sound, setting a powerful precedent for the entire Renaissance. This Western triumph of individual genius over structural dogma, however, stands in fascinating contrast to the architectural philosophy emerging in the East, where builders sought not to dominate their materials but to achieve a profound harmony with the natural world. Far from the rigid stone of European cathedrals, ancient Japanese builders worked with a living, breathing material, wood. They understood that to fight against nature was to invite destruction, so they chose instead to dance with it. In a land constantly shaped by earthquakes, they developed a form of architecture that did not resist seismic force, but absorbed and dissipated it. The most stunning example of this is the traditional pagoda, a structure that appears so delicate, so seemingly fragile, yet has survived violent tremors for over 1,000 years. The secret lies not in nails or glue, but in the breathtaking complexity of timber joinery. Master craftsmen carved intricate, interlocking joints that fit together with the precision of a fine puzzle. These joints were not rigid locks, they were designed to allow for a subtle, controlled movement. During an earthquake, the entire structure could sway and shift, the wood flexing and the joints groaning as they redistributed the immense forces throughout the framework. This prevented stress from concentrating at any single point, the primary cause of catastrophic collapse in rigid buildings. It was a system of organized flexibility, a concept modern engineers now call ductility. At the very heart of the most resilient pagodas rests another stroke of genius, the shinbashira. This is a large, central pillar that runs through the core of the building, but it is not firmly attached to the structure. Instead, it hangs like a massive pendulum, suspended from the top or resting loosely on a base stone. When an earthquake strikes, the floors of the pagoda can sway independently in a figure 8 pattern, while this heavy central column swings in the opposite direction, acting as a counterweight that stabilizes the entire building. This is not merely an ancient technique. It is a direct, functional precursor to the base isolation systems we use in modern skyscrapers and hospitals today, where an entire building is placed on flexible bearings to decouple it from the shaking ground. How did these builders, without seismographs or computer models, arrive at such a profoundly advanced solution? Their knowledge was born from centuries of careful observation. They watched how tall, flexible trees weathered storms and tremors by bending, not breaking. They learned through trial and error, studying which joints held and which failed, passing this empirical wisdom down through generations of master carpenters. This approach was as much a philosophy as it was an engineering principle. It reflected a deep reverence for nature, a belief that a building should exist in harmony with its environment, moving with the earth rather than defiantly standing against it. This mastery of wood and movement demonstrates a different path to innovation, one of subtle adaptation rather than forceful domination. Just as Japanese joinery found strength in flexibility, another culture discovered immense power in the perfect, timeless forms of pure geometry. This pursuit of harmony through geometry finds a different voice in the intricate silence of the Alhambra Palace. Here, walls and ceilings dissolve into a mesmerizing tapestry of interlocking stars, swirling vines, and complex polygons, each pattern repeating into infinity with no discernible beginning or end. This was the genius of Islamic architects who broke from the tradition of figurative art to explore a deeper spiritual truth through pure mathematics. For them, these endless tessellations were not mere decoration. They were a direct reflection of the infinite and omnipresent nature of the divine, a visual representation of a universe without start or finish, governed by a single, unifying order. To create such perfection required a staggering command of advanced algebra and trigonometry. Master artisans worked with compasses and straightedges, employing star polygons and intricate grids to generate patterns of breathtaking complexity. They understood that true beauty resided in perfect proportion and symmetry, embedding mathematical constants and relationships into the very fabric of their designs. Yet this artistry was often deeply practical. The repetitive, interlocking nature of these geometric networks frequently served a structural purpose. By distributing forces evenly across a vast surface, much like the fractal patterns we use in modern, lightweight engineering materials, these delicate-looking stone screens could help stabilize walls and ceilings. In spaces like grand mosques, the complex surfaces also played with sound, breaking up sound waves to modulate acoustics and reduce echoes, allowing the spoken word to carry with clarity. This intuitive grasp of multidimensional space, of creating visual fields that suggest dimensions beyond the physical three, was a form of Chinese letter that Western mathematics would not formally explore for centuries. What inspired such a profound fusion of equation and aesthetics? It was a worldview that saw no separation between science, art, and faith. The architect was a geometer of the soul, using the universal language of mathematics to craft an earthly paradise that hinted at the eternal. This legacy of dynamic pattern is not confined to history books. You can see its direct influence in the algorithms that generate digital art and the parametric designs shaping contemporary architecture, proving that a rule broken in 14th century Granada can still resonate in the silicon of today. This exploration of pattern as a dynamic force finds its dramatic counterpart in the next great upheaval, where architecture would shed its static form to embrace motion, emotion, and theatrical spectacle. But the quest for perfect geometry soon gave way to an architecture of pure emotion. Walk into a Baroque church and the very walls seem to breathe, curving and swelling as if the stone itself has become a living, dynamic force. Architects like Francesco Borromini consciously shattered the serene balance of the Renaissance, rejecting static symmetry in favor of a controlled chaos designed to overwhelm the senses. He employed concave and convex forms, creating undulating facades that play with light and shadow in a constant, rhythmic dance. The ground plans of his buildings were often complex ovals or elongated hexagons, shapes that deny the viewer a single, fixed perspective. Your eye is forced to move, to follow the curves, to explore the space as an active participant rather than a passive observer. This was a radical departure from architecture as a fixed object. It was architecture as an event, a performance in stone. To achieve this theatrical fluidity, Baroque masters manipulated materials in astonishing ways. They made heavy plaster appear as billowing clouds and carved marble to mimic soft, flowing drapery. This was not merely decoration, it was a deliberate blurring of the lines between reality and illusion, challenging the very nature of the materials they worked with. The ultimate expression of this was the quadratura, where painters and stucco workers collaborated to make ceilings dissolve into open skies, with figures soaring upward into an infinite heaven. This total integration of sculpture, painting, and architecture created a fully immersive, multi-sensory environment that enveloped the visitor. It was the 17th century equivalent of virtual reality, a complete narrative space designed to tell a story and evoke a specific, powerful emotional response from awe to pious devotion. The psychological impact was meticulously crafted through the masterful use of light and shadow, or chiaroscuro. Windows were strategically placed to create dramatic pools of illumination that highlighted central altars or sacred sculptures, while leaving peripheral areas in mysterious gloom. This contrast did not just enhance spatial depth, it actively guided your movement and focus through the interior, manipulating your attention and your feelings with the skill of a stage director. How did these artists achieve such complex illusions without any digital aids? Their tools were profound empirical knowledge of perspective, painstaking craftsmanship, and a fearless willingness to bend visual rules in the service of a greater emotional truth. This Baroque spirit, which prioritized experience over pure form, would eventually provoke a dramatic swing of the pendulum, as a new generation looked back to the sober principles of antiquity for a different kind of revolution. That Baroque drama of emotion could not last forever. A new generation of architects looked upon the swirling forms and theatrical excess and called for a return to reason, to clarity, and to the sober principles of classical antiquity. This was the birth of neoclassicism, a movement that seemed to be about looking backward, but in truth was a quiet revolution that broke the rules of its own present by resurrecting the distant past. They rejected the complexity of Baroque and Rococo, finding a new ideal in the clean lines, geometric harmony, and dignified proportions of ancient Greece and Rome. Yet this was not a simple act of copying. It was a reinvention, a fusion of ancient ideals with the emerging engineering science of the 18th century. In Paris, Jacques-Germain Soufflot embodied this spirit with his design for the Church of Saint Genevieve, now known as the Pantheon. From the outside, it is a temple of pure reason, with its majestic portico of Corinthian columns and its soaring dome, a direct homage to the Roman Pantheon. But inside, Soufflot performed a feat of modern engineering. He wanted to achieve a breathtaking sense of lightness and space, to flood the interior with light in a way the heavy Roman originals never could. To do this, he secretly incorporated a skeleton of iron rods and chains within the stone structure. These metal reinforcements acted like an internal brace, reducing the thickness of the piers and allowing for larger, more open arches and vast window openings. This was a hidden innovation, a precursor to the reinforced concrete that would define the next century. Soufflot was using the industrial material of his age to achieve a classical vision of perfection, creating a building that appeared timeless on the surface but was utterly modern in its bones. This neoclassical movement was about more than just aesthetics. It was deeply philosophical. It reflected the Enlightenment values of order, logic, and civic virtue. Architects were no longer just building palaces for kings or churches for the clergy. They were designing libraries, museums, and government buildings meant for the public. Their work was part of a grand urban planning effort to create cities that were accessible, orderly, and beautiful, spaces that would elevate the human spirit through proportion and light. How did these architects balance such a strict historical homage with such forward-thinking techniques? They understood that the true spirit of the classics was not about slavish imitation, but about rediscovering the fundamental principles of stability, harmony, and human scale. By looking back with fresh eyes, they found a path forward, proving that innovation can sometimes mean returning to first principles and rebuilding them with the tools of a new era. This elegant fusion of iron and stone, of old forms and new functions, set the stage for a far more dramatic rupture, as the world stood on the brink of an industrial age that would shatter all previous notions of what a building could be. The elegant fusion of iron and stone was a whisper compared to the thunderous declaration made by the Crystal Palace. In 1851, Joseph Paxton, a gardener by trade, did not just design a building, he grew one from a catalogue of industrial parts. He looked at the heavy, permanent traditions of masonry and saw only limitation. His radical idea was to build a palace of air and light, a structure so vast it enclosed full-grown trees, yet so transparent it seemed to vanish against the London sky. This was architecture as a kit of parts, a concept that broke every rule of permanence and craft. Paxton employed a system of standardized, prefabricated iron components, all mass-produced in factories and assembled on-site with breathtaking speed. The entire monumental structure, covering an area larger than 10 football fields, was erected in just a few months. This modular approach was a direct precursor to the way we construct buildings today, from corporate skyscrapers to suburban homes, proving that efficiency and beauty could be partners. The framework was a marvel of lightweight strength, a grid of slender iron ribs that supported over 300,000 panes of glass. This skin of glass transformed the interior into a sun-drenched conservatory on a colossal scale, a world where the boundary between the built environment and the natural world simply dissolved. Visitors could walk through this luminous nave, surrounded by fountains and foliage, under a ceiling that was the sky itself. This blurring of inside and outside was not just an aesthetic choice, it was a new philosophy of space, one that directly influences the greenhouses, shopping malls, and glass atriums that define our modern landscape. How did a gardener conceive of such a radical architectural vision? Paxton's genius was born from his daily work with greenhouses. He had spent years designing glass structures to protect delicate plants, learning how to maximize light and manage humidity. He applied this exact same logic to the Crystal Palace, treating it as the largest greenhouse ever built, one designed to shelter not just plants, but the entire industrial might of the British Empire. His cross-disciplinary thinking demonstrated that the most profound innovations often arrive when we step outside the silo of our own expertise. The palace was also a statement on temporality, designed for the Great Exhibition and later dismantled and moved. It championed the idea that architecture could be adaptable, scalable, and even temporary, principles that are now central to our modern pursuit of sustainable and prefabricated design. Paxton proved that true rule-breaking could be as simple as looking at a factory-made iron beam and a sheet of glass and seeing the future. This celebration of industrial materials, however, would soon provoke a beautiful rebellion as a new movement sought to soften the machine's hard edges with the flowing, organic lines of the natural world. That celebration of the machine's hard logic could not entirely suppress the human desire for something softer and more alive. A quiet rebellion began to bloom, quite literally, from the pavements of Paris. At a Hector Guimard-designed metro entrance, cast iron does not form a rigid arch. Instead, it writhes and curls, twisting into the sinuous stems of orchids and the delicate tendrils of vines, as if the entrance itself has organically grown from the city's soil. This was the heart of Art Nouveau, a movement that broke from the rigid geometries of industry by declaring that a building should feel as dynamic and natural as a living organism. Architects turned away from the straight line and the perfect circle, drawing inspiration instead from the asymmetric beauty of a flower stem, the gentle curve of a river, and the intricate patterns of insect wings. They believed that true beauty was found in nature's flowing lines, and they sought to weave that vitality directly into the fabric of the city. To achieve this unprecedented fluidity, they embraced the very materials of the industrial age, but used them in entirely new ways. Exposed iron was no longer hidden as a structural skeleton. It was celebrated, forged into those plant-like forms that defined the style. Massive, custom-made glass panels were curved and shaped to fill the openings within these organic frames, allowing light to flood into interiors that felt like enchanted grottos or sun-dappled forests. This was not a rejection of modern materials, but a reinterpretation of their potential, prefiguring our modern concepts of biomimicry, where designers look to nature to solve complex engineering and aesthetic problems. This movement was also a profound stand against the growing uniformity of mass production. Each Art Nouveau building was a unique work of art, celebrating the hand of the craftsman. Elaborate wrought iron, custom ceramic tiles, and intricately carved woodwork were all integrated into the design, making every doorway, every window frame a one-of-a-kind statement. In this sense, they were the spiritual ancestors of today's custom digital fabrication, where technology enables a return to personalized, highly detailed design rather than standardized, identical units. Beyond the facade, this philosophy transformed the interior experience. Rooms were no longer a series of boxy compartments. Spaces flowed seamlessly into one another, with arched openings, curved walls, and staircases that swept upward like unfolding blossoms. This was architecture that considered how a person moves through and feels within a space, prioritizing comfort, aesthetic pleasure, and a sense of harmonious flow. What drove this beautiful rebellion against the straight line and strict symmetry? It was a yearning for a more human-centric and emotionally resonant environment, a direct response to the perceived coldness of the industrial world. This embrace of nature's beautiful chaos, however, would soon be challenged by a new generation of thinkers who believed that true progress lay not in ornament, but in the radical purity of function. That beautiful rebellion of flowing lines and natural forms was soon met with a stark, white wall. In Vienna, architect Adolf Loos looked upon the ornate facades of his city and saw not beauty, but a primitive and criminal waste. He declared that ornament is a crime, a shocking statement that broke from centuries of decorative tradition in a single, sharp pronouncement. His Steiner house stands as a silent monument to this radical idea, its facade a pure, unadorned geometric form. This was not a mere aesthetic preference, it was a moral and philosophical stance. For Loos, the urge to decorate was a sign of a less evolved culture, and the modern era demanded a new honesty, one where beauty was found not in applied decoration, but in the inherent qualities of the materials and the pure expression of a building's function. This radical shift embraced the new industrial materials of reinforced concrete and steel, not by twisting them into organic shapes, but by celebrating their inherent strength and logic. The result was a new architectural language of clean lines, flat roofs, and crisp, white surfaces. The building structure was expressed openly and honestly, with no need for false columns or sculpted garlands to hide its true nature. This concept of truth to materials would become a cornerstone of modernist architecture. The modernists introduced a revolutionary idea, focusing on volume over mass. Instead of constructing heavy, solid walls that defined a building as an impenetrable object, they thought in terms of defined space. They used planes and surfaces to carve out volumes of air and light, creating buildings that felt light and open. A key tool in this was the ribbon window, a long, horizontal strip of glass that could run the entire length of a wall. This was a complete departure from the punched window openings of the past. It dissolved the corner of a room, blurring the boundary between inside and outside and flooding the interior with even, diffused light. Inside, the open plan became the new ideal. Walls were liberated from their load-bearing duties by the steel or concrete frame, allowing spaces to flow seamlessly into one another. Rooms were no longer rigid, box-like cells but flexible zones for living. This was a profound rethinking of domestic life, prioritizing spatial flexibility and a connection to the surrounding environment. How did this dramatic rejection of ornament reflect broader cultural changes? It mirrored the 20th century's accelerating pace, its embrace of industry, and a growing desire for clarity and efficiency in a complex world. This minimalist ethos was not about emptiness, but about creating a calm, rational backdrop for modern life. The pioneers of this movement, like Luz and later Le Corbusier with his famous declaration of a house as a machine for living in, introduced ideas of minimalism and functional efficiency that resonate powerfully in our contemporary design, from the clean lines of a smartphone to the open-plan layouts of today's offices and homes. Their work demonstrated that by stripping away the unnecessary, architecture could achieve a timeless power. And yet, this very pursuit of pure function would soon find its most spectacular contradiction in the work of an architect who believed that the greatest function of all was to embody the wild, untamed beauty of nature itself. Antoni Gaudi's buildings seemed to breathe and grow like something alive, a stone forest sprouting from the streets of Barcelona. His masterpiece, the Sagrada Familia, is the ultimate rebellion against the straight line, where columns branch overhead like ancient trees and vaults ripple with the complex curves of hyperbolic paraboloids. Gaudi broke from the rigid constraints of Euclidean geometry by turning to nature's own engineering playbook. He understood that a tree's branching structure is perfectly optimized to distribute weight, and that bones use minimal material for maximum strength. To translate these biological principles into architecture, he employed a method that was as brilliant as it was unconventional. In his workshop, he constructed intricate models from hanging chains and small sacks of lead shot. When suspended, these chains naturally formed perfect catenary arches, the ideal shape to handle pure compression. By inverting this model, he could design arches and vaults that channeled gravity's forces with flawless efficiency, a structural calculus worked out in real space with string and weight long before computers could perform the same calculations. This intuitive process allowed him to create ruled surfaces and double-curved forms that were not only breathtakingly beautiful but also astonishingly strong, using geometry that would not become commonplace in architecture for another century. Inside the Sagrada Familia, the forest of columns does more than just hold up the roof. Each one is inclined to better carry its load, just like the angled trunks of trees resisting the wind, a concept that prefigures the parametric design software used by architects today. His use of color and texture was equally revolutionary. He covered surfaces in trencadis, a vibrant mosaic made from broken ceramic tiles and discarded glass, transforming industrial waste into a shimmering skin that catches the light and dances with color. This created a fully immersive, sensory environment where structure, ornament, and light are fused into a single spiritual experience. What inspired this profound synthesis of Gothic aspiration and biological wisdom? Gaudi believed that the great book of architecture was always open, written in the patterns of nature itself. He looked beyond human-made systems to the deep, enduring wisdom of forests, skeletons, and honeycombs, proving that the most radical innovations often come not from inventing something new, but from rediscovering the ancient, optimized logic of the world around us. His legacy challenges us to see every tree not just as a plant, but as a masterclass in structural engineering. This deep respect for local, almost living materials invites us to consider how other builders found genius not in imported resources, but in the very earth beneath their feet. Gaudi's profound connection to his local environment finds a powerful echo in the timeless wisdom of vernacular builders across the globe. In the scorching deserts of ancient Persia, architects confronted an impossible climate not with force, but with a gentle, brilliant manipulation of the air itself. They constructed tall, slender wind-catching towers or badgers that rose high above the city skyline. These were not decorative spires. They were sophisticated natural ventilation systems, engineered to trap the slightest breeze from any direction and funnel it down into the heart of the home below. This incoming cool air would sweep across a pool of water or a fountain, chilling and humidifying before flowing through the living spaces, pushing the hot, stale air out through opposite openings. It was a form of architectural respiration, a building that could breathe and cool itself completely without any need for electricity. This was a radical departure from simply importing a style or a technique from another region. It was a deep, context-specific innovation born from a direct and intimate dialogue with the local environment. These builders broke the most fundamental rule of all, the idea that architectural progress meant adopting universal, foreign methods. Instead, they looked to the ground beneath their feet and the sky above their heads for answers. They employed materials like sun-baked mud, brick, and thick, insulating thatch, substances that were not just sustainable and affordable, but perfectly tuned to their purpose. Mud brick's high thermal mass absorbs the intense heat of the day, preventing it from penetrating the interior, and then slowly releases that warmth during the cool desert night. This natural regulation creates a stable, comfortable indoor climate, a principle we now call passive cooling, which is a cornerstone of modern green building. The entire layout of a traditional Persian house was a lesson in environmental harmony. Central courtyards provided private, shaded oases, with surrounding rooms oriented to capture favorable breezes and block dust storms. Intricate systems of qanats, or underground canals, brought water from the mountains for both drinking and cooling the air in the courtyard gardens. This was an integrated, holistic approach to resource management, an intuitive grasp of thermodynamics and hydrodynamics that our current sustainable architecture is only now rediscovering and formalizing as bioclimatic design. How did these vernacular builders, often anonymous and working without global knowledge exchange, achieve such profound efficiency? Their laboratory was daily life, and their methodology was generations of accumulated observation. They learned which wall thickness kept a room coolest, which roof shape shed rain most effectively, and how to position a window to catch the winter sun but avoid the summer heat. This knowledge was passed down through practice and tradition, becoming an inseparable part of the local culture. This approach naturally fostered community as well. The shared courtyard was not just a climate tool, it was a social heart, a place for families to gather in the cool of the evening. The construction itself was often a communal effort, with craftsmanship honed over lifetimes, embedding cultural identity into every hand-laid brick and woven roof. This demonstrates that rule-breaking does not always require a singular, rebellious genius. It can be a collective, culturally rooted wisdom, a slow and steady refinement of form in perfect response to place. This deep respect for the honest expression of local materials, however raw, would later inspire a very different movement that found its own stark beauty in the unadorned truth of concrete. That stark beauty in raw, local materials found its ultimate expression in a movement that treated concrete not as a skeleton to be hidden, but as a skin to be celebrated. Brutalism erupted from the post-war landscape with the force of a geological event, its massive, monolithic forms declaring a new kind of honesty. Architects like Le Corbusier broke from the sleek, polished finishes of early modernism by leaving their concrete completely exposed, a technique known as béton brut, which means raw concrete in French. This was the core philosophy of the movement, a radical commitment to truth in materials. The concrete was not a mistake to be covered with plaster or paint. It was the authentic, final surface, bearing the imprints of the wooden boards it was poured into, with every seam and grain visible. This texture told the story of its own making, a permanent record of the construction process itself. The material's plasticity allowed architects to sculpt it into vast, monumental shapes that conveyed an immense sense of strength and permanence, a powerful symbol of rebuilding and resilience for societies recovering from the devastation of global conflict. These buildings were not designed as delicate objects. They were landscapes, mountains of human habitation that prioritized function and social vision above all else. Le Corbusier's Unité de Habitation in Marseille is a prime example, a vertical city designed to house thousands. Its sheer scale was a statement of belief in collective living and social housing. But within this massive block of raw concrete, the architect embedded a revolutionary idea for community. He included an entire internal street with shops, a hotel, a school, and a rooftop gym and running track. Elevated pedestrian pathways connected different sections, all designed to foster social interaction and create a self-contained neighborhood in the sky. This was a direct challenge to the isolated, single-function zoning of many cities, and its influence is clearly visible in today's mixed-use developments that combine residential, retail, and public spaces in a single project. Why did such a socially ambitious movement become so divisive? Brutalism's uncompromising aesthetic challenged every conventional notion of beauty. Its heavy, imposing forms and rough textures were often perceived as cold and inhuman. Yet this was precisely the point. Brutalist architects were emphasizing substance over style, structural truth over superficial decoration. They argued that the beauty was in the building's honest expression of its purpose and materials, in its powerful geometry and the dramatic play of light and shadow across its deeply textured surfaces. How is it that this once maligned style is now experiencing a major revival? A new generation is rediscovering brutalism's powerful presence and social idealism, seeing in its rugged forms a refreshing authenticity in a world of glossy, commercial facades. The very raw concrete that was once scorned is now valued for its tactile, timeless quality. This embrace of a building's unvarnished truth of its sheer physicality pushes the architectural imagination to consider an even more radical proposition. What if a city was not a static collection of buildings, but a living, breathing entity that could grow, adapt, and metabolize like a natural organism? That idea of a city as a living, breathing entity found its boldest expression in the dreams of post-war Japan. A group of young architects calling themselves the Metabolists looked at the ruins of their cities and saw not a blank slate but a biological opportunity. They proposed a radical new rule to break, that a building or a city must be a permanent, static monument. Instead, they envisioned urban structures that behaved like living organisms, capable of growing, evolving, and even shedding parts over time. At the heart of this philosophy was the core and capsule concept. A permanent, robust megastructure, like a tree trunk or a spine, would serve as the core, containing all the essential services like elevators, plumbing, and power. Onto this core, individual living capsules, like leaves or cells, could be attached, replaced, or upgraded as needed. This was architecture with a life cycle, designed for change rather than obsolescence. The most iconic and now poignant example is Kisho Kurokawa's Nakajin Capsule Tower in Tokyo. Each of its 140 capsules was a self-contained living or office unit, prefabricated in a factory and then bolted onto the central concrete cores. These capsules were not meant to last forever. The revolutionary idea was that every 25 years or so, they could be individually unbolted and swapped out for newer, more advanced models, allowing the building to regenerate itself without being demolished. This was a profound statement on sustainability and resourcefulness, a direct challenge to the wasteful cycle of construction and destruction. What inspired this powerful biological metaphor in a nation recovering from war? The metabolists were driven by a futuristic optimism, a belief that architecture could and should keep pace with the rapid technological and social changes of the modern world. They saw the city as a dynamic ecosystem, not a fixed plan. Their use of lightweight, industrial materials and flexible connections was not just an aesthetic choice. It was a practical system for creating adaptable, human-centric environments that could respond to the flux of urban life. The legacy of metabolism is a powerful reminder that our buildings are not separate from nature's processes. They encourage us to think of a city not as a collection of finished objects, but as a constantly evolving entity, a garden of structures that can grow and change with us. This vision of architecture as a dynamic, technologically integrated system naturally set the stage for a movement that would proudly wear its mechanical heart on its sleeve. That industrial honesty found its ultimate expression in a building that wore its guts on the outside. The Centre Pompidou in Paris erupted onto the scene like a playful industrial machine, a declaration of war against the very idea of a discrete facade. Architects Richard Rogers and Renzo Piano performed a stunning architectural inversion, taking all the elements a traditional building hides within its walls: the escalators, the air conditioning ducts, the water pipes, the electrical conduits, and boldly displaying them on the exterior. This was not an attempt to prettify the machine, but to celebrate its raw, functional logic as a new form of beauty. By stripping the interior of this complex circulatory system, they achieved something revolutionary: a vast, open, and completely flexible floor plan, an empty canvas where the art inside could dictate the space, free from the obstruction of columns and fixed service cores. This design choice broke the most fundamental rule of civic architecture, that a cultural temple should be a dignified, impenetrable monument. Instead, the Pompidou was a living diagram, an educational tool that invited everyone to see how a building really works. The color coding of its exposed surfaces was a language in itself: blue for air, green for water, yellow for electricity, and red for circulation and safety, transforming a technical schematic into a vibrant public spectacle. How did high-tech architecture challenge traditional notions of beauty and function? It argued that truth could be as beautiful as illusion, that the elegant solution of an engineering problem possessed its own profound aesthetic. This philosophy was built on a foundation of prefabrication and precision. Components were manufactured off-site and assembled with the logic of a kit, emphasizing efficiency, quality control, and the potential for future adaptation or even disassembly. This foreshadowed our current priorities of sustainable construction and circular economies, where buildings are designed for their entire life cycle. The movement's core belief in transparency and exposed structure directly influences today's green architecture, where thermal mass is left visible to regulate temperature and renewable energy systems are integrated as proud features of the design. By making the building's functions visible and understandable, Rogers and Piano created a deeply interactive experience, turning every visitor into an unwitting student of infrastructure. This celebration of the mechanical, however, would soon give way to an architecture that questioned whether order and logic were even possible at all. That celebration of mechanical logic was shattered into 1,000 glittering fragments. Frank Gehry's Guggenheim Museum in Bilbao does not greet you with a predictable facade. Instead, it surges from the riverbank like a colossal, titanium-clad flower, its petals curving in a chaotic, breathtaking dance. This is deconstructivism, an architectural movement that took the rulebook of structural harmony, tore it to pieces, and reassembled it into something entirely new and disorienting. Architects like Gehry and the visionary Zaha had consciously broke from the rectilinear grid, creating forms that appear to be in a state of explosive motion or controlled collapse. Their buildings challenge our most basic perceptions of space and stability, evoking a sense of dynamic disruption rather than serene order. This was not random chaos, but a carefully calculated rebellion. The philosophical roots of deconstructivism reach deep into 20th century thought, drawing from the literary theory of deconstruction, which questions the stability of meaning and reveals hidden contradictions within seemingly solid systems. In architecture, this translated to a rejection of traditional binaries like inside versus outside, structure versus ornament, and even beauty versus ugliness. A Zaha-Hadid building, such as the Haydar Aliyev Center in Baku, embodies this perfectly. It presents a continuous, flowing surface where the wall becomes the roof, and the interior space bleeds seamlessly into the exterior landscape. There are no clear edges, no comforting right angles, only a single, fluid gesture frozen in concrete. This was a direct critique of rigid social orders and a bold embrace of the complex, fragmented nature of contemporary life. How were these seemingly impossible forms actually built? The answer arrived with the digital revolution. Deconstructivist architects were among the first to fully harness the power of computer-aided design, or CAD, an advanced three-dimensional modeling software. These digital tools allowed them to visualize and engineer wildly complex, non-rectilinear shapes that would have been unthinkable with traditional drafting boards. The computer became their sketchbook, and the calculations required to keep these gravity-defying structures standing were handled by algorithms. To bring these digital dreams into reality, they turned to advanced materials and fabrication techniques. Jerry's team used software originally developed for the aerospace industry to model the Guggenheim's intricate titanium panels, each one uniquely shaped and then precision cut by computer-controlled machines. This process of digital fabrication, where design data directly drives manufacturing, has since become standard practice, influencing everything from product design to custom furniture. The deconstructivists proved that the most rebellious artistic vision could be realized through a partnership with cutting-edge technology, blurring the line between architectural sculpture and functional building. Their work forces us to ask, can a building that challenges our sense of stability actually make us see the world in a new way? This spirit of radical rethinking, of questioning every foundational assumption, naturally extends beyond form to function, pushing us to reconsider architecture's most fundamental relationship, its pact with the natural world. A building that produces more power than it consumes sounds like science fiction, yet it stands today in the heart of Seattle. The Bullitt Center is a living testament to a new kind of architectural rebellion, one that breaks from the energy-intensive norms of the 20th century, not with grand gestures, but with a quiet, profound efficiency. Its designers asked a simple, radical question. Why can a building not function like a forest, contributing to its ecosystem rather than draining it? To answer this, they integrated a canopy of solar panels that transforms the roof into a power plant, rainwater harvesting systems that make the building self-sufficient for water, and even composting toilets that treat waste as a resource, not a problem. This is the essence of sustainable architecture, a movement that prioritizes passive design above all else. Instead of fighting the climate with massive heaters and air conditioners, these buildings work with it. They are oriented to capture the low winter sun for warmth and shaded to block the high summer sun, using the sun's own path as a thermostat. Walls with high thermal mass, much like the ancient mud brick structures of Persia, absorb heat during the day and release it at night, creating a stable, comfortable interior without any mechanical help. Natural ventilation is engineered into the very form, with strategically placed windows and vents that create cooling cross breezes, allowing the building to breathe on its own. The materials themselves tell a story of localism and low impact, sourced from nearby forests and manufacturers to slash the environmental cost of transportation. This is not just about reducing a carbon footprint. It is about creating a building that actively enhances the health of its occupants, flooding spaces with natural light and using non-toxic materials for cleaner indoor air. How can sustainable design learn from historical rule breakers? The answer lies in their shared philosophy. Just as Japanese builders observed trees to withstand earthquakes and Persian architects studied the wind for cooling, today's sustainable pioneers are looking back to these ancient principles of bioclimatic design and supercharging them with modern technology. Green roofs, which insulate and manage stormwater just as a layer of sod did on vernacular huts, are now sophisticated ecosystems. Smart grids allow buildings like the Bullitt Center to talk to the power network, selling excess energy back during sunny periods. This approach reconnects architecture with the ecological systems it had long ignored, promoting not just environmental resilience but community well-being by creating healthier, more self-reliant urban spaces. This deep integration of building and environment, of ancient wisdom and cutting-edge tech, naturally pushes the boundaries of what is physically possible to build, leading us into a realm where the very process of construction is being reinvented through digital fabrication. That quiet, profound efficiency of sustainable design demands a new language of form, one that can only be spoken by the machine. A facade composed of thousands of unique ceramic tiles, each one slightly different from the next, curves and folds to shade a building from the sun, its pattern generated not by a human hand but by an algorithm responding to solar path data. This is the world of parametric design and digital fabrication, a revolution that breaks the most fundamental rule of the industrial age, standardization. Architects like Greg Lynn no longer draw a single, fixed shape. Instead, they design the system that generates the shape. They write algorithms, sets of rules and parameters that define a building's form based on specific performance goals, structural loads, and environmental conditions like wind and sunlight. The computer then calculates millions of potential variations, discovering the most efficient, elegant solution, a form that is organically complex and perfectly tailored to its purpose. This process allows for mass customization, where every component can be unique without incurring prohibitive cost. Think of it as growing a building rather than assembling identical parts. The resulting geometry, often flowing and intricate, resembles the optimized structures found in nature, like the porous bones of a bird or the layered petals of a flower, achieving immense strength with minimal material. How is this digital process changing the very role of the architect? The designer becomes less a master draftsman and more a conductor of computational forces, setting the initial conditions and then curating the forms that emerge from the digital ecosystem. This technological leap is made physical through digital fabrication. 3D printing builds up structures layer by layer from metal or polymer, creating complex hollow forms that are both lightweight and strong. Computer numerically controlled, or CNC, milling machines carve massive blocks of foam, wood, or stone into precisely sculpted components with a level of detail impossible for human craftsmen. Robots, guided by the same digital model, can then assemble these thousands of unique pieces with unerring accuracy. This democratizes fabrication, allowing small studios to realize designs that were once the sole domain of massive engineering firms. We are witnessing a shift from construction as assembly to construction as cultivation, where a building is the physical printout of a complex digital equation. This deep integration of data and material naturally pushes us to ask where the next boundary lies. inviting a closer look at how architects are not just using algorithms, but are beginning to collaborate directly with the logic of life itself through biomimicry. The logic of life itself is now a blueprint for the buildings of tomorrow. Deep within the African savanna, a termite mound stands as a masterclass in climate control, maintaining a constant, cool temperature despite the scorching heat outside. Architect Mick Pierce looked at this natural marvel and asked a revolutionary question: why fight the environment with expensive, energy-guzzling machines when we can collaborate with it? His answer, the Eastgate Center in Zimbabwe, broke from every convention of sealed glass box construction. Instead of relying on power-hungry air conditioning, he designed the building to breathe like its insect-inspired counterpart. The structure features a network of chimneys and ducts that harness the simple principle of convection. Hot air naturally rises and escapes through the top, drawing in cooler air from below in a continuous, self-regulating cycle. The building's concrete structure acts as a thermal sponge, absorbing coolness overnight and slowly releasing it throughout the day. This ingenious system uses only 10% of the energy of a conventional building its size, creating a comfortable interior environment for thousands of people at a fraction of the cost. This is the core of biomimicry, a philosophy that steps beyond human-centric solutions to seek answers in nature's deep-time laboratory. It applies 3.5 billion years of evolutionary research and development to our most pressing architectural challenges. The results are not just efficient, they are profoundly resilient. Consider the Namibian desert beetle, which survives in an arid landscape by collecting drinking water from the air. Its shell has bumps that attract moisture and troughs that channel it toward its mouth. Scientists and architects are now designing building facades that mimic this exact texture, creating surfaces that can harvest fresh water from morning fog or humidity, turning a building into its own utility. Other innovators are studying the self-shading qualities of forest canopies to design facades that open and close in response to the sun, much like leaves adjusting to light. What can these ancient organisms teach us about future-proof design? They demonstrate that the most elegant solutions are often passive, decentralized, and seamlessly integrated within their ecosystem. A building becomes not an isolated object, but a participating member of a local ecology. This deep respect for natural intelligence moves us beyond simply using less energy and toward creating structures that actively contribute to the health of their surroundings. This philosophy of adaptation, of learning to thrive within a changing world, leads us directly to the next great challenge for the rule breakers, designing for a climate that is itself becoming increasingly unpredictable. That same spirit of adaptation is now being tested by our planet's shifting climate. Along the Dutch waterfront, a quiet revolution floats upon the water. These are not houses designed to stubbornly resist the flood, but to gracefully yield to it. Amphibious homes rest on fixed foundations, yet during a flood, their hollow bases allow the entire structure to rise with the water, bobbing safely on the surface like a boat at its mooring. When the waters recede, the houses gently settle back into their original positions. This is a fundamental break from the idea of a static, immovable foundation, embracing a dynamic and responsive relationship with the environment. Resilient architecture accepts that the threat is real, and instead of building taller walls, it builds smarter systems. These designs incorporate redundant systems, ensuring that if one fails, another takes over. Think of a building with multiple power sources, perhaps solar panels and a backup generator, or water purification systems that can function independently of the main grid. The materials themselves are chosen for their ability to endure, from impact-resistant glass that can withstand flying debris to flexible jointing that allows a structure to sway without shattering. This philosophy does not start from scratch. It revives and re-engineers ancient wisdom. Stilt houses used for millennia in flood-prone regions are a clear precursor, raising living spaces above the waterline. Ancient systems of terraced farming and intricate irrigation managed water flow and prevented erosion in ways we are only now fully appreciating. Modern resilience takes these historical concepts and supercharges them with advanced engineering, creating structures prepared for sea level rise and the intensifying fury of superstorms. This approach extends beyond the building itself to the very fabric of the city. Green infrastructure turns the urban landscape into a sponge. Instead of channeling rainwater through concrete pipes, it creates parks that double as water retention basins, permeable pavements that allow water to seep back into the earth, and restored wetlands that act as natural buffers against storm surges. These are not just amenities, they are vital organs in a city's circulatory system, managing water naturally while providing cooling green spaces for communities. How can we build cities that not only survive but actually thrive in these changing conditions? The answer lies in viewing adaptation not as a burden, but as an opportunity for innovation. This forward-thinking approach finds a powerful ally in the unexpected revival of one of humanity's oldest building materials, one that connects our past security directly to our future survival. The same earth beneath our feet is now being stacked into the walls of our future. A quiet rebellion is reshaping the skyline, not with new alloys, but with the rediscovery of ancient materials like rammed earth, adobe, and mass timber. Architects are consciously breaking from the century-long dominance of steel and concrete, materials with a notoriously high carbon cost, and are instead looking back to create a more sustainable and humane built environment. They are not simply replicating the past, but fusing timeless techniques with modern engineering and material science. The result is architecture that feels both ancient and futuristic, grounded in local context yet globally relevant. Consider the humble rammed earth wall. It is made by compacting layers of damp soil, often mixed with a small amount of stabilizer like lime, into a formwork. When the forms are stripped away, the result is a beautiful, striated surface with the texture of sedimentary rock. This wall is not just a partition, it is a massive thermal battery. Its high thermal mass naturally absorbs heat during the day and releases it at night, creating a remarkably stable indoor climate with minimal need for mechanical heating or cooling, just as it did in vernacular structures for millennia. But today, engineers can precisely calculate its compressive strength and seismic performance, allowing it to be used in modern applications its original builders never envisioned. An even more dramatic shift is happening with wood. For decades, we built tall with steel and concrete, seeing wood as suitable only for small-scale houses. That perception has been shattered by the development of cross-laminated timber, or CLT. Imagine sheets of lumber stacked crosswise and glued together under immense pressure, creating solid wooden panels with the strength and rigidity of concrete slabs. These panels can be prefabricated off-site and then assembled with astonishing speed, like a giant, precise puzzle. A building made from CLT is not just a structure, it is a carbon sink. The wood locks away carbon dioxide for the life of the building, actively fighting climate change with every floor that is added. This allows for the creation of serene, warm interiors that connect occupants directly to nature, a stark contrast to the cold, hard surfaces of conventional high-rises. What is driving this profound return to pre-industrial materials? It is a convergence of environmental necessity and a deep human longing for authenticity. In a world of homogenized glass boxes, a rammed earth wall carries the unique color and character of the local soil. A timber beam reveals the history of a forest in its grain. This revival is not about nostalgia. It is about reconnecting buildings with local heritage, craftsmanship, and a tangible sense of place. It demonstrates that the most forward-thinking solution might be to reach back and reclaim the wisdom embedded in the very earth and forests we have long taken for granted. This deep respect for material authenticity and local context naturally extends to a more profound question of who our buildings are truly designed to serve. A building's true purpose is not just to shelter bodies, but to nurture a community. This conviction drives a quiet revolution in socially equitable design, where architects break from profit-driven models to focus squarely on human well-being. The most radical act is to hand the blueprint over to the people who will actually live there. Through participatory workshops and collaborative planning, future residents become co-designers, ensuring the final space reflects their real needs, culture, and daily rhythms. This process results in public housing that prioritizes community gardens over barren parking lots, universal accessibility that welcomes everyone regardless of age or ability, and shared resources like tool libraries and childcare spaces that foster mutual support. The goal is to design out isolation and design in connection, creating environments that actively foster social cohesion and reduce inequality. This philosophy materializes in innovations like co-housing, where private homes cluster around abundant common spaces, encouraging spontaneous interaction and a shared sense of responsibility. Flexible living units can adapt to a family's changing size or an individual's shifting mobility, preventing disruptive and costly moves. An even more profound development is trauma-informed design, which uses architecture to promote psychological safety. This means avoiding institutional, labyrinthine corridors that can feel threatening, and instead using clear wayfinding, calming colors, and access to natural light to create spaces of dignity and calm for survivors of adversity. This entire approach has deep roots, drawing inspiration from historical visions like the Garden City movement, which sought to blend the benefits of town and country. But today's rule breakers update that ideal with contemporary insights into equity, justice, and public health. They ask a fundamental question: how can a simple wall or window become a tool for genuine social change? The answer lies in recognizing that every design decision, from the placement of a bench to the choice of a tree, either builds a barrier or opens a door. This profound focus on human experience and collaborative creation is now being amplified by a tool that allows us to walk through a design long before the first brick is ever laid. That profound focus on human experience now finds its ultimate tool in a realm of pure potential. Architects are no longer confined to drawings and scale models. They can now step directly into their own designs, walking through a building long before its foundation is ever poured. Virtual reality technology shatters the limitations of two-dimensional blueprints, allowing designers to inhabit a full-scale simulation of a space. They can test sight lines from a future occupant's perspective, checking if a column blocks a key view. They can assess the acoustics of a concert hall, listening to how sound carries and reverberates in the digital void. This is a fundamental break from the abstract guesswork of the past, replacing it with an embodied, sensory understanding of a design's impact on the human experience. The process becomes deeply iterative and collaborative. Teams scattered across the globe can meet inside the same virtual model, pointing out changes and experimenting with materials and lighting in real time. A client who may have no technical training can put on a headset and truly understand the architect's vision, walking through their future home or office and providing meaningful feedback before a single truckload of concrete arrives. This collaborative power makes architecture profoundly more democratic and accessible, breaking down the barriers of technical jargon and allowing communities to have a real voice in the designs that will shape their lives. This virtual immersion is supercharged when linked with building information modeling, the sophisticated digital DNA of a modern building. The virtual model is not just an empty shell. It is an intelligent system packed with data. Architects can now run simulations within the virtual environment, watching how sunlight moves through the space at different times of the year, analyzing energy performance, and even modeling how people might naturally flow through the corridors during peak usage. This allows for a new kind of optimization, where a design is refined not just for its aesthetic appeal, but for its efficiency, comfort, and social functionality. How is this transformation reshaping our conception of the built world? It accelerates creativity by removing the fear of costly errors, encouraging bolder, more innovative forms. It shifts the entire profession toward a more user-centered philosophy, where the final building is a product of deep empathy and rigorous testing, rather than just an architect's solitary vision. These virtual tools are the latest expression of that enduring spirit of rule-breaking, proving that the most radical designs are now being born not on paper, but in a world of light and data. These architectural visionaries, from Imhotep's first stone steps to the algorithms shaping our digital realms, share a common thread of courage. They looked at the established rules of their day and saw not boundaries but invitations to innovate. Their legacies are not locked in history books, but are living testaments to a powerful truth that genuine progress rarely comes from following a well-worn path. It emerges from the boldness to ask difficult questions and the resilience to embrace ideas that others might dismiss as impossible. The challenges we face today, from a rapidly changing climate to the intense pressures of urban growth, demand this same revolutionary spirit. We are called to build not just for shelter, but for resilience, for community, and for a sustainable coexistence with our planet. The lessons from these rule breakers are our blueprint. They inspire us to design with vision, to prioritize inclusivity, and to see every building as an opportunity to heal rather than harm our world. Let their stories be a spark for your own creativity. Whether you are designing a city, a product, or simply navigating the complexities of daily life, remember that the future is not something that happens to us. It is built piece by piece by those who dare to see a different possibility and have the conviction to bring it to life. If this journey through the mysteries of architectural genius has inspired you, we would love to hear your thoughts in the comments below. Subscribe to join us as we continue uncovering the hidden stories that shape our world. The next great innovation is waiting, not in a distant time, but in the mind of someone willing to reimagine the possible.